Thanks for hopefully still being awake at this time in the afternoon, and thanks to the organizers for having me. My name's Phil Taranto. I'm currently based at the University of Tokyo, and today I'm going to be talking maybe a little bit something somewhat left of field, considering I probably won't use the word energy or Hamiltonian. But it's about characterizing and controlling quantum processes with classical memory. And I'm going to argue at some point that it is quite relevant for optimizing some sort of energetic or computational tasks. So it's a work that's been done recently in collaboration with Marco Tullio Quintino and my supervisor at Todai, Mio Morale, and Simon Mills. So I just want to start off by setting the scene and saying that memory is really the fundamental form of temporal complexity in processes. So we can think of all sorts of different complexities in states or in processes. And as has been alluded to by many of the talks earlier in this conference, I like to think of, let's say there's sort of two sides to the same coin when we think about memory. If it's something that's present in a process, but we're not able to control it, we usually like to call it noise. In particular, when it's complex memory, we think of it as non-Markovian noise. And this makes processes inherently difficult to model. Some examples are stuff like weather patterns, finance markets, predicting biochemical reactions or whatever. On the other hand, as many of you have also talked about, if we can control the memory of some kind of process, actually it becomes like a resource, right? We get some potential advantage. Some instances of this you might be familiar with. We routinely see protocols involving complex feedback or optimizing of control parameters, which routinely outperform cases where we don't have control over the memory. So whether we see it as noise or whether we see it as some kind of resource depends a little bit on the controllability of the memory. And maybe just as a brief example of a type of application that might be somewhat relevant to some of you in the conference, could think of something like quantum dots, where we could imagine maybe being able to control not just the state of the dot at some point in time, but really the memory and being able to feed forward information about past states to enhance certain charge transport or something might be able to help us to build better efficiencies in solar cells or whatever. So just processes and states of matter or whatever themselves can be classical or quantum in nature depending on their behavior, the memory effect itself can also be classified as being either classical or quantum. That's what I'm going to be talking about. And this is because memory effects at a physical level, they really stem from or are transmitted by interactions between the system and its environment. So we've heard a lot of talk about environments impacting the dynamics of certain processes. And that's, of course, the case. That's really what gives rise to memory. And going back to, for example, this quantum dot instance, you could think of your quantum dot sitting in between some kind of electrodes. Maybe it's coupled or talking to even some nearby quantum dots or other systems. And everything that's around it basically constitutes the environment. And in general, the state of that environment is going to be interacting with your system, and it's also going to influence its future dynamics, and so on and so forth. So this is how memory effects build up in physical processes. And really what I want to get through here is that the environment is what acts as the memory carrier. And it's basically the dynamics of the environment which lead to what kind of memory effects that you see on your system. Okay? And the second point that I want to get across as a kind of motivation or something that's kind of interesting to study is really this idea of multi-time correlations. So in this nice paper, which was done in the group of Cavan by a previous PhD student, Roberto, they recently published this nice paper where they were looking at the dynamics of a quantum dot blinking in time. And there they saw some interesting phenomena where there were some classical memory effects in the dynamics. And there were really memory effects that are unable to be explained by just looking at the transition rates of your dynamics alone. So the point that I want to get across here is that this means there's fundamentally multi-time memory effects happening. The current state of the system, or even maybe one past state of the system, isn't enough to tell you anything about, or well, not the full story, let's say, about the future dynamics. So you really need to look at the dynamics over multiple points in time. And so these are very, very complex memory effects that we have here. And aside from those sort of, let's say, theoretical or a little bit practical motivations, maybe another kind of motivating point here would be that looking at quantum processes where the memory effect is classical in nature, which is what I'm going to focus on for the rest of the talk, potentially the ones that somehow promise some kind of near-term applicability, let's say. So on the one hand, they're like more powerful than their memoryless counterparts. So if you think about processes with no memory, they're kind of simple, so to speak, at least in theory, to deal with. On the other hand, you have like processes with fully quantum memory that might be very powerful, yes, but they're super difficult to engineer, this kind of coherently controlled feed-forward protocols or something like that. So the ones in between, which are these kind of like quantum systems but controlled by classical memory, they sort of fit within the sweet spot somehow and might be the ones that we could like in the near term engineer, because at least the memory itself is kind of stable over long periods of time. So in principle, we might be able to control it better. Even if the system is kind of like decohering quickly, it might give still some advantage. So hopefully that sets a little bit of a motivation for why we want to study these. And interestingly, at least from my perspective, is that the distinction between like quantum processes with either quantum memory or classical memory hasn't really been so well studied or even looked at, even in theory. So besides some kind of simple cases. So that was kind of my motivation for looking at it. I thought it's an interesting problem. And throughout the talk, I'm going to basically put forth, a couple of different candidates that might be a suitable definition for classical memory quantum processes. And then with that at hand, kind of go forth and characterize them from a theoretical perspective. So that hopefully gives some kind of like, underpinning to seeing what these kind of processes could be useful for. So, okay, multi-time quantum processes and different types of memory. What exactly am I talking about? I'll try to be a bit more precise now. So I'm always picturing in my head basically a kind of open system dynamics where you have some system S, which is coupled to some environment I just call E, okay? And they're going to be like correlated initially. They're going to, build up entanglement through the dynamics over time. And in particular, I'm thinking of a picture like this where I always pick a discrete set of times, let's say, 1, 2, 3, where I can do whatever I want to the system. So I can always like address my system in theory. So could make a measurement there or whatever. And by the word multi-time, I basically just mean something where there's more than 2 times. So 2-time description, many of you are probably familiar. You have like a quantum channel taking input state to output state. This is something like a next level of generalization of that, where you can really probe your system at many points in time, and you can really start to look at like multi-time correlations in what you observe. That's the basic picture. Yes, and now I'll talk a little bit about different types of memory. So the one, like I mentioned earlier, it's what happens to the environment that dictates what kind of memory effects you see on your system. So for one example, basically, you could think of if my environment evolves coherently in between every part of dynamics, let's say, for instance, by like an identity channel I've drawn up there, then it can, of course, like transmit quantum information, let's say, coherently through time, and you really have like a quantum memory process. On the other hand, the other kind of extreme is if your environment really rapidly dissipates all information about your system and completely forgets about it and it never comes back. That's a memoryless process, or Markovian one. And we can, we typically model this, at least in our head, by thinking like, in between each step of my dynamics, my environment is being just discarded and prepared as a fresh state, which is uncorrelated to anything that happened before. So there's really no way for any temporal correlations to happen in such a process. So now, like I've been talking about, basically this point that, what happens to the environment really greatly influences your system dynamics. Of course, that's true. One kind of crucial point to note is that Nevertheless, we can really distinguish between different types of memory only by looking at the system dynamics. Okay, so we don't need to model the full system environment dynamics. Of course, that's impossible. We can kind of do these like generalized process tomographies, or even look at like kind of witnesses of memory or non-Markovianity, where we just look at the system and can understand and distinguish between different types of memory. And we do that by, or well, let's say one tool that allows us to do that, maybe the theorists of you might know something about this, like there's a kind of Choi-Yamilkovsky isomorphism where you can map your any, let's say, dynamics onto a state for a channel that's mapping a two-time dynamics to a two-party state. For a multi-time process like this, it maps like to a many-body state. But nevertheless, just by looking at the system alone, we can start to distinguish between these two things. So I'm going to be kind of thinking within this framework. Details don't really matter, but suffice to say, just by looking at the system, you can start to distinguish memory effects. So in the top case, we really have this, when we have quantum memory, we have like a many-body entangled, temporally entangled process. That's like the most difficult one to deal with, let's say. In the bottom case, like I said, where we don't have any memory, we end up with a simplified structure of a process that has no temporal correlations. So basically, we end up with this sequence of independent channels taking our dynamics from one step to the next. And the fact that that those portions are independent really reflects the fact that there's no memory in our process. So they're the two kind of extreme cases. And then now I get to like the crux of, let's say, what we're looking at, which is classical memory quantum processes. So these are going to be like something in between. And yeah, after like studying and thinking about these things a little bit, I realized there's a few different potential candidates for what we're talking about here, actually. So one of them, which was the first thing that kind of came to mind in some sense, and others have also put forth this kind of definition, which is to say something like, imagine that your environment is subject to an entanglement breaking channel between every step of dynamics. So for instance, that could be something like, you know, you could think of the environment being measured and then re-prepared. And because it's re-prepared, like for some, you know, classical label X, it can feed forward some classical information through the environment. So this gives like a really good, like, let's say, physical picture mechanism of how classical memory might be transported. Problem is trying to characterize the set of this kind of processes turns out to be the most difficult one. So it's one of those situations where like, it's the one that's operationally meaningful, but it's somehow the most hardest to deal with. But okay, let's leave that definition there. Another potential definition, which leads to a much simpler set of processes, it turns out, is what I call classical direct cause. This is a kind of simple picture also. You could imagine that there's a referee, they flip a coin. When it lands heads, they send you one memoryless process. When it lands tails, they send you another one. Because you don't know the coin flip distribution, then you're going to see some memory effects in your dynamics. So it has some kind of classical memory in it. And that set of processes is like kind of easy to characterize since it's basically the convex hull of all memoryless processes there. And the third type of processes are the ones which represented by separable choice states. So I mentioned briefly this kind of like many-body choice state of your process. You can look at that and just ask the question, is that separable or not? So we have these three kind of candidates for classical memory processes. And I'm just going to jump a little bit ahead to the kind of main results. Or, yeah, those are all of the processes that I've just put forth. Basically, snapshot of this slide is to say that as we go down the kind of ladder here, it seems that we're adding more constraints mathematically onto the type of processes. So we should be able to distinguish between them in some kind of hierarchical fashion. But I would point out, like, the story is not so simple as it seems, because some of the lower constraints within the set of processes imply higher constraints sometimes. So an example of this is like for two-time processes, those classical memory processes with the entanglement breaking channel and the coin flip ones, they end up being equivalent. So, yeah. And then there was another interesting point where trying to distinguish between those processes with separable choice state and those actually implementable by classical memory measure and prepare channels on the environment, they were conjectured to be non-equivalent in this paper by Giamazzi and Costa some time ago. And then they couldn't prove it, and then later it was proved that they're actually non-equivalent. But basically, I just wanted to say that these papers also kind of inspired a lot of my work looking at these, and wanted to say that it showed that it's really non-trivial to distinguish between these things. And that leads me to basically the last slide, which is the main result of our paper, which is to really distinguish between all of these sets of processes in the multi-time case. So whenever you have more than 2 time steps, that hierarchy, you can distinguish between these different types of classical memory processes just by looking at the system. And the way that we do it is actually introducing another set of processes, which are non-signaling processes, which I'll just very briefly describe. They are basically processes for which, if you throw away your system state at some point in time and prepare it fresh, that action deletes all possible memory effects that you could potentially see. And this is somewhat related to memory effects in processes, but like not fully. And in fact, we show, maybe you can see in this picture, like there is no hierarchy between non-signaling processes, separable processes, and classical memory processes in general. So they're a little bit different, but they allow us to distinguish between some of these processes. So that's basically the end of the talk. I'm going to jump into some outlook and conclusion points. To summarize quickly, we showed this kind of, in the multi-time setting, there's really a kind of rich tapestry of memory effects that we can see. So I would, implore people to look more into these things. And we were able to distinguish them by looking at the different types of signaling properties, how information can signal forward through in time. And one last thing to mention, in the paper, we also provide a kind of toolbox of computational methods that let you kind of approximate these sets of processes. Many of them are kind of SDPs, so they're efficiently implementable. And for Outlook, what I would be interested in is kind of trying to concretely connect some of these sets of processes to information processing tasks that, that certain sets might be optimal for, because that would really characterize them in terms of their usefulness. And the last thing would be we've been looking at this kind of discrete time picture, and I'm interested in thinking about what kind of continuous time dynamics lead to these different sets of memory. So thank you very much for your attention.
Thank you very much. I think maybe we have time for one ultra-fast question, but we're a bit
sorry for being a bit over time.
But, all right, very quick. Yes.
So if I understood correctly, you can use this isomorphism to make a representation between memory and states. So for those states that have no memory, for those processes that have no memory, you have like perfectly separable states or like product states.
Actually, product, yeah.
Product states, exactly. And in the case of quantum memory, you have entangled states.
Yeah.
Can you say something for the intermediate case? Maybe you did mention it, but I'm not sure if I understood. Like, if you have classical memory, do you also have classical type of correlations?
Yeah. So all classical ones cannot be entangled. So basically that largest set of the 3 definitions of classical memory ones that I proposed, the largest set are not entangled states, so separable states basically. And the smaller subsets are kind of restricted forms of separable states. So yeah. Mm-hmm.